Hello everyone. We have been discussing Chapter 3 of A Student's Guide to the Great Physics texts. And in this chapter, which is called Archimedes' Principle and Falling Bodies, Salviati and Simplicio and Segredo are discussing the speed with which objects fall. So when you drop a ball, how fast does it go? What they've been discussing so far is Aristotle's view on the speed of falling objects. You might remember that according to Aristotle's theory, at least as reported by Galileo, this is Aristotle's theory, is that if you drop an object, it's going to, at some point in time, achieve some maximum speed, and this speed is proportional to the weight of the object, of the body that you're dropping. That's point one. And point two is that the velocity of the falling object is proportional to 1 over the density of the medium through which you're dropping it. 1 over the density of the medium through which you're dropping it. So a denser medium means a slower velocity of fall. That's Aristotle's theory. And what is happening is Salviati is critiquing this theory. And what he's been focusing on so far is this first point here. He's been showing that if you really take Aristotle's theory correctly, you're going to run into some contradictions or some difficulties. And that's what we talked about in our last lecture. At this point, what happens in the discussion is that Simplicio just kind of pipes up. He says, come on, you're arguing that Aristotle's wrong. But we all know that if you drop a cannonball, it is going to hit the ground before a tiny bird shot, right? So a very tiny grain of lead, you drop it and you drop a cannonball next to it. We all know the cannonball is going to hit first. And that's exactly what you'd expect from Aristotle's theory, that somehow the speed of the object depends on the weight of the body. And this is actually true. So what Salviati mentions on page 33 is that you are correct. The cannonball is going to hit the ground first, but it is not going to hit. It's pretty close to the same time. It's going to hit just a little bit ahead of the bird shot, whereas if Aristotle was correct, then it should hit drastically ahead of the bird shot. If the velocity really is proportional to the weight of the body, the cannonball weighs much more than the body, it should fall at a much greater speed and hit the ground way before. But the fact is, they hit the ground at pretty close to the same time. Okay? So what we have to do is think a little bit more carefully about the factors that go into the speed of falling objects. So let me ask this question, and this is the question that Salviati, Segredo, and Simplicio begin to explore. First of all, they wonder, does the density of the object, not just the weight, but the density of the falling body affect its speed of fall? So that is, if you take iron and drop it, and wood and drop it, they have different densities. Actually, they don't use the term density, they use the term specific gravity. And specific gravity is kind of another term for density. What it is, it's the density of the object compared to the density of water. So an object with the exact same density as water would have a specific gravity of 1. An object with twice the density of water would have a specific gravity of 2. So they speak in terms of the specific gravity of substances. So iron has a greater specific gravity than wood does. Okay? So the question is, does the density or the specific gravity of the falling body affect its speed of fall? And secondly, so that's maybe question 1. And question 2 is, does the density of the medium, through which the object falls affect its speed? Through which the body falls affect its speed. Okay, so remember the argument of Aristotle is that it does, the density of the medium does affect its speed, and it's an inverse relationship. Okay, So let's assume, so these are the two general questions that are going to be asked here. So let's assume for the moment, assume that Aristotle point 2, that's this point right here, point 2 is correct. Let's just assume that's correct for the moment. What does this imply, or what would this imply? So remember in the last lecture we looked at point 1 and Salviati showed that this implies some internal contradictions. Now we're going to look at point 2, and again what we're going to find according to Salviati is that point 2 also implies contradictions. So let's explore that for a few minutes. Okay, and so what we do is let's argue in this way. This is the way that Salviati presents it. Suppose that we have some object that's made of wood, a ball that's made out of wood, and we drop it. Suppose we drop a wooden ball or a wooden sphere, okay? If we drop a wooden ball and we ask how fast does it fall? Well, of course, we're going to get into this in a little more detail later. Of course, when you drop it, it starts out with no speed and it accelerates, it gains speed, but at some point it's going to get to some final speed when you drop it. And what we're really asking is what's its final speed when you're dropping it? And specifically what Salviati asks Simplicio is, if you drop a wooden ball, let's just throw out a speed that it's going to have. What do you think the speed it's going to fall at? And Simplicio says, okay, this is, by the way, page 34. Simplicio says, let's just take the velocity of the wood ball falling in air to have a value of 20. We're just going to assign a number to the speed it has when falling through the air. It doesn't really matter whether or not this is correct or what units we're using. We're just assuming there is some speed, and we'll call that a speed of 20. Okay? Now, having said that, point 2 is suppose we drop that wooden ball in water and we take Aristotle's theory correctly. So suppose now we drop the same ball, the same wooden ball. My laptop is frozen up again. We drop the same wooden ball in water. What does Aristotle's theory imply about its speed? So what does Aristotle point 2, this right here, what does Aristotle point 2 imply? Well, we can form a ratio. The velocity of the wood in water compared to the velocity of the wood in air. What's the ratio of those two speeds? Well, because according to Aristotle, the speed goes as 1 over the density of the medium, the ratio of the wood in water to the wood in air should go as the inverse ratio of the densities. So the density of air compared to the density of water. I'm using a Greek letter rho here for density. Okay? So again, because if we assume that the velocity goes inversely as the density, then the ratio of the densities the ratio of the speeds should go as the inverse of the ratio of the densities. And what is the density of air compared to the density of water? Well, we don't know offhand, but let's just, I think in the text they say, let's just suppose it's 1/10. Air is much less dense than water. Let's just throw out 1/10. That's not quite right, but let's just assume that to be the case. Now, what would that imply? That would imply that the velocity of the wood in the water is going to be equal to 1/10 the velocity of the wood in the air. So if we take this formula right here and we move the wood in air up to there, we get velocity of the wood in the water is 1/10 the velocity of the wood in the air. But we assumed the velocity of wood in the air is 20, so the velocity of the wood in the water would be equal to 2. Okay, that would be the implication of what we're saying here. Now, why is this a problem? This is a problem is because wood floats. Wood doesn't sink at all in water, but wood floats in water. And our theory just suggested that if it falls in air, it's going to fall in water just with 1/10 the speed. That's not true, so this cannot be correct. Notice that Galileo here is not presenting his own theory here. All he's doing is showing that there are problems with Aristotle's theory. So he's offering a critique of Aristotle. Okay? So let me pause here for a minute, and then I'll come back and we'll talk about one more critique regarding this.